the cooling of beverages, the expansion of the universe, the inevitability of death. All of these ideas are innately linked to the concept of entropy. Now, you may have heard of it described as disorder or chaos, but fundamentally, entropy is about asking questions. So say you ask me a question like, what number will this dice roll? By finding the answer, you're going to gain a certain amount of information. In information theory, entropy is a measure of how much information you get on average. This is innately linked to the idea of probability. Say I had a die which was very biased and only rolled a 6 every single time. By finding the answer to the previous question, you aren't actually gaining any information, so entropy equals 0. Now, if we take this slightly harder example of the entropy of a perfectly fair die, with a probability of 1/6 for each face, it can be kind of hard to figure out what information would mean. But the revolutionary computer scientist Claude Shannon reasoned that the amount of information of a state would be equivalent to the minimum number of yes or no questions you'd have to ask to figure out that state. I'm illustrating this on this chart here. Now, if you look a little bit more generally, you will see that because of the yes or no question, each level splits into 2 more in the lower level. So based off of this, we can predict the number of questions based on the log base 2 of 1 over the probability, if there's an equal probability of everything. Now, for cases where there isn't an even probability, if you had a slightly biased dice, then you could take a weighted average by multiplying by the probability. And if we sum all of these different values, then we have a general formula for the entropy. This is called the Shannon entropy, and it's the center point of information theory. Now let's apply our knowledge of entropy to thermodynamic systems, like ideal gases. In thermodynamics, we talk about macrostates and microstates. A macrostate is what we can measure from the outside: pressure, volume, temperature, etc. The microstate is all the different individual positions and velocities and movements of the particles inside the gas which enable those macrostates which we measure. You can liken the macrostate to the overall configuration of a die, and the microstate to each individual face of the die. Knowing all this, we can take the Shannon-esque Gibbs entropy with its extra constant K Boltzmann, which is really just a conversion factor between ordered and disordered energy, and assume that every microstate is equally likely, and land with the great grand Boltzmann entropy. Well, that's it for my foray into entropy. I hope you liked this video and will continue studying this forefront of modern physics. Thank you.